Hello guys, in this lecture we're going to do a follow-up on our previous MATLAB tutorial for visualizing the dynamics of forward of serial manipulators. And I'm going to come back to the code which we had developed last time, right? And the whole code basically was built based on Lagrangian dynamics. So what we did is we expressed the kinetic energy of the robot by looking at the linear the translation of kinetic energy, right? And then we also looked into the potential energy. So this is my total potential energy, my total kinetic energy. Then we solved this Lagrangian basically in MATLAB. Obtained two equations of motion. We obtained angular accelerations on every joint. And then basically we set up a loop and we solved for the angular acceleration in real time. Then we numerically solved for the angular velocity, and then one more integration, and then we ended up with the joint position. And we did actually simulate that. And today, what I would like to do is let's continue working on this exercise, but let's actually validate a little bit of the dynamics. So what I'll do is this is what I had from last time. What I did add is simply add a torque. I added a torque to the equations of motion, EOM1 and EOM2, and that comes from basically Lagrange. So this is your QI, right? Or these are the non-conservative forces that are applied. So either you are, adding energy to the system by applying, force or a torque or whatever it is, or it would be friction, right? And remember, if this is a rotational degree of freedom, then it should be torque. And if this is a translational degree of freedom, then this guy would be force. So I didn't really change this at all, other than simply adding the torques. I'm going to go ahead and run it, but what I'll do is, let's see it. So this is the dynamics of the system. Now, let us go ahead and add some damping to it. So what I can do is in my loop, basically, so the torque is basically now in angular acceleration. I can put the torque after if I want, or before. Before would be a bit more accurate over like one time step, but it wouldn't make a difference. So if I want to add some damping, basically what I can say simply is if I put torque is equal to minus omega 1, it means that I'm applying a torque against the angular velocity. So, angular velocity always define a motion. If the angular velocity is positive, it means this joint is going in, the positive direction. If it's negative, it's going to be moving in the opposite direction. So if I put the torque to be equal to minus omega 1, basically, I'm adding a frictional torque, correct? On joint 1. And similarly, I can do on the other one, torque 2 is equal to minus omega 2, right? And again, I had these already defined here. I solved my equation of motion, and then I recaptured the angular accelerations. So let's come back here and then run it. Okay, well, what's going on? Okay, well, we put it minus 2, so basically we're literally adding a torque, right? So what we want to do is, okay, minus omega 2. There you go. But I want to put it here, so it's stay consistent. So this is my damping here, and where B is equal to 1, that may be a lot of torque, okay, a lot of frictional torque, so there you go. So this is basically damping, right? And I can basically make it like 0.1 here, 0.1 here, and now basically 0.1 is the value of my damping. And you see, now we have a bit of oscillations as a result of adding damping. All right. Now we actually have the dynamics of the robot, right? We have the dynamics of the robot, so I can actually add a torque here, right? Let's say I have a motor, right? The torque of the motor is equal to KTI, where I is a current, and KT is torque constant. What if you have a constant current, for example, applied, and that is resulting in a torque of 0.5 Newton meter? So let's run it. So you see, basically, it's actually trying to resist the motion a little bit. If I increase that a bit more, and if you want to stop the code at any time with MATLAB, all you have to do is click Control, hold Control, and then click C. Right? You can stop the code. So literally now I'm applying this torque. Now it's going to accelerate it. Right? it's going to accelerate it, but then you have a torque that is a function of omega. So to actually reach a steady state velocity, which is what we are seeing right now. Sometimes the video is slowing down is because I'm sharing the screen basically from Zoom. So it's resulting in this movement. Okay, great. So now let's also do one more thing. Let's actually verify the computational dynamics of the system. So I want to revert back to 0. And what happens if you increase the time step, right? So here you are calculating alpha, which is your angular acceleration. You are numerically integrating your angular acceleration. What happens if your time step is a bit large, right? If your time step is large, you will actually result in, your integration is not very accurate anymore, right? Because your steps are larger. And what happens actually, the system will actually become unstable as a result of increasing the time step. And that error will actually increase over time. So if I let the system play around for a bit, you will see that at some point it will actually, it will become fully unstable. Right. So basically, it's like you are adding energy into the system. You see now we are adding more energy, so on and so forth. Okay, so I'll stop it here. And to verify this, what we can do is we can actually look at the energies, right? So at any moment, based on Lagrange dynamics, the kinetic energy, the total of the kinetic energy and the potential energy must be equal to a constant value. Well, how do I get the kinetic energy and the potential energy from here? Well, I can only get them from here. Well, I already have them earlier, right? So this is my total potential energy. And so let's pull it. So this is my potential energy. Control T, and then this is my kinetic energy, right? So let's actually do this whole thing. And then capture my T and then my V. So let's actually stop the code here and then run it. And there you go. Basically, this is your total kinetic energy, and then this is your total potential energy. So literally, these are now functions of all the variables that we've already calculated, right? So I'm gonna put it here. So this is my total kinetic energy. And now, how about my total potential energy? It's right here. Okay, so now we do actually have our total kinetic energy. Let's come back here with debugging. We highlight these. Now run the code. Basically, you will actually, at any moment, you actually have your potential kinetic. So what I can do is I can actually do E, or my total energy, as equal to T plus P. And I can actually either view it or I can plot it, right? So this is my total energy. You see that the energy is basically, as a result of this, my energy is fluctuating, and at some point it's, that energy has to be constant. It can't change, right? So if it's changing, basically there's something wrong. So what you can do is you will decrease the time step. And I think 0.05 is accurate. And by the way, MATLAB is not really real time. So when you pause dt, it doesn't really actually pause by that time. Why? Because it takes, when you tell MATLAB to pause for dt, right? Even though here it's actually pausing for dt, but you actually have to take into account the cost of running this code, right? So running this code will actually take time. Okay, now the energy is changing, but it's changing much less. Over time, and if you continue to do this, so as you can see now, the energy is not really changing by much. So the total energy is sort of, because certain dynamics are actually accurate. So here's what we can do now. So we don't actually need to do this anymore. Let's go ahead and then start doing a little bit of controls. So here's my torque. And if let's actually increase the time step a little bit, because every time you reduce the time step, it will actually result in the system not playing. It will basically clog the system. So what I'll do is I'm going to go ahead and set up a controller here. And what I can do, one thing is I can actually set up a proportional controller. And I can do torque is equal to Kp theta 1 desired minus my actual theta 1. If I do this, now the robot is actually going to try to actually maintain a theta desired, right? And I already specified my theta desired to the power over 4. And I'm going to do the same thing on second one here. 2 minus theta 4. All right, so now if I actually run that, the robot, let's actually reduce my Kp and then make it 1. You see basically the robot is going to fall down, right? But then it's actually, the controller is trying to take it to this position, right? And there's no KD, by the way, for now. We don't have any KD implementation. If I increase my Kp to 5 and see what happens, basically, you see basically the robot is trying to go to power 4 on joint 1, right? So joint 1 is power 4. Okay, now. Okay, what I'll do is I can reduce my Kp, right? And let's see what happens. So you see basically it's trying to reduce the error, but as a result of the inertia, right? Your controller is basically applying a force, but the inertia is resulting in that spring type or effect on the dynamics, right? So you have a balance. So you apply torque, you add inertia to you apply torque, basically you add acceleration. Acceleration is often velocities. And the velocity basically, obviously, increases the energy of the system. Then the torque will try to balance it, and then that actually results in this unstable behavior. What we can do is we can actually add a KD to it, like a damping. And KD basically, it's going to be omega. So theta 1 desired, right? So, I could try to, for example, maintain a velocity, or I could track a moving angle, for example. In this case, it would be 0 if I have a fixed set point. And here, what is the derivative of theta 1? It's going to be minus omega 1. We already have that. So this is the beauty of converting this problem into an algebraic problem. So KD minus omega 2. So basically, now we have actually added some damping over here, and let's actually run it. Oops, we don't have KD defined, so let's define it again. There you go. So here we go. So we've added some damping to the system, right? We have to actually increase our Kp, correct? So I'm going to actually make this 10, and now let's run it. So you see, basically now we're actually controlling the robot, right? And then we're asking theta 1 to be power over 4. I could actually ask this to be power over 2, so it's going to make a vertical position, and then the other one's going to be 30 degrees with horizontal. So let's do that. I'm sorry, 30 degrees with respect to the first joint, right? Because that's how we define our theta 2. If I want to make this power over 2, it will actually be like a bracket, right? Like this, and that's going to come back over. So there you go. And you can also, you can see basically there is a bit of deviation. Why? Because we don't have Ki on here, right? We're not going to be covering Ki because it would require us to integrate the error. But here's, this is simply an example of doing this in real time. What we can do as well is we can actually try and change the masses. So if I actually increase the mass on link 2, right? Because we have it in the middle. Let's say if I make it 0.5, you'll see basically you will actually have more inertia for the system, and that's going to be a little bit more difficult for it to actually, compensate for the errors, right? All right. So this is how you can basically implement a basic, PD controller on a robot, on a 2 degrees of freedom robot. Any questions, guys? Please don't hesitate to email me, and I'll be very happy to go over these with you and explain to you anything that you don't understand.